So now let's look at stage 2, which is the condition where the concrete cracks. So this is more like a point on the moment curvature diagram. And we're looking at the instant the concrete cracks in tension, which means that this epsilon tension, the strain and tension at the bottom, is equal to the rupture strain or the tensile rupture strain of concrete. This mathematical definition here just says concrete cracks. All the other materials, the steel and the concrete and compression, remain linear elastic. So really the definitions are the same as before in terms of strains, so that the steel has not yielded and the strain in compression of the concrete is still less than the proportional limit of concrete in compression, and this just implies linear elastic material behavior. And the only difference again is that the tensile strain at the very bottom is equal to the concrete rupture strain and tension. The analytical approach is the same as stage 1 because we're going to analyze this as though the instant just before this tensile strain is equal to the tensile rupture strain of concrete. So our analytical approach really has one major goal. Given this strain value, what applied moment results in this strain profile and this stress profile? And the moment associated with this first crack is called the cracking moment, which we call MCR. And really the way that this problem might be laid out is that, or this analysis might be laid out, is that you're given that epsilon tension is equal to epsilon r, and by Hooke's law you could say, what the stress in tension is at this instant, which really is equal to the modulus of rupture or the tensile strength of concrete. And depending on if you're using the ACI code, this is just equal to 7.5 square root of FC prime. It's just a material property. It's the tensile strength of concrete. Then you would go ahead and use the flexure formula. This stress profile would still apply, but you would know this stress value here, and you can back calculate the moment using the flexure formula, which would just be FR times I, and I'm going to say gross over Y, the distance to that tensile fiber. And again, it's easier to do this if you ignore the steel, but if you don't ignore the steel, then you have to use the transformed area method, calculate the centroid, and go through the process, and that'll give you a more accurate result if you include both steel and concrete. But typically you can get a close enough estimate if you ignore the steel. And that is stage, or point 2 really. And now what we want to do is move on to stage 3. And I would say we're going in order of least importance to most important. So stage 3 I would consider the second most important stage. Stage 4, where we have ultimate behavior, where the concrete strain reaches the compressive rupture strain, that's the most important because that's the stage or point where we design to.